When dealing with a 200 amp electrical service, selecting the appropriate ground wire size is a critical safety consideration. The requirement that the ground wire be the same size as the phase conductors, or larger, is a fundamental principle in electrical wiring. In the scenario where the phase conductors are number 4 wire, it is imperative that the ground wire also be number 4 or larger. The purpose of the grounding system is to provide a low impedance path for fault current to return to the source. This path facilitates the rapid operation of overcurrent protective devices like circuit breakers or fuses, which quickly disconnect the circuit and prevent electrical shock or fire hazards. An undersized ground wire can impede this process, leading to dangerous conditions. The National Electrical Code, NEC, provides specific guidelines and tables for determining the correct size of grounding conductors based on the size of the service entrance conductors. These tables take into account factors such as the ampacity of the conductors and the type of grounding system being used. Consulting the NEC is essential for ensuring compliance with safety standards and preventing electrical hazards. In most residential applications with a 200 amp service, the service entrance conductors are often number 4 or larger depending on the specific load calculations. Therefore, the grounding electrode conductor, which connects the service equipment to the grounding electrode system, must be sized accordingly. The grounding electrode system typically consists of a grounding rod, a ground ring, or connection to a metallic water pipe. The size of the grounding electrode conductor is determined by NEC Table 250.66, which correlates the size of the service entrance conductors to the required size of the grounding electrode conductor. It's crucial to differentiate between the grounding electrode conductor and the equipment grounding conductor. The grounding electrode conductor connects the service equipment to the grounding electrode system, while the equipment grounding conductor provides a path for fault current from equipment enclosures back to the service equipment. The equipment grounding conductor is sized according to NEC Table 250.122, which is based on the rating of the overcurrent protective device protecting the circuit. In the case of a 200 amp service, the equipment grounding conductor for branch circuits would need to be sized appropriately based on the overcurrent protection for each individual circuit. Using an undersized ground wire can have several detrimental effects. Firstly, it can limit the amount of fault current that can flow back to the source, which may prevent the overcurrent protective device from operating quickly enough to clear the fault. This can result in prolonged exposure to high voltage and current, increasing the risk of electrical shock or fire. Secondly, an undersized ground wire can overheat during a fault condition, potentially melting the insulation and creating a fire hazard. The heat generated by the fault current is proportional to the resistance of the conductor, and an undersized conductor has a higher resistance, leading to more heat generation. Thirdly, an undersized ground wire may not provide adequate protection for sensitive electronic equipment. Electronic devices are susceptible to damage from voltage surges and transients, and a properly sized grounding system can help to mitigate these effects by providing a lower impedance path for the surge current to dissipate. In addition to ensuring that the ground wire is properly sized, it is also important to ensure that it is properly installed. The ground wire should be securely connected to the service equipment and the grounding electrode system using approved connectors and methods. All connections should be clean and tight to minimize resistance and ensure a reliable electrical connection. It is also important to protect the ground wire from physical damage, as any damage to the conductor or its insulation can compromise its effectiveness. Regular inspections of the grounding system are recommended to identify and address any potential problems before they become a safety hazard. These inspections should include checking for loose connections, corrosion, and physical damage to the conductors and connectors. Any problems that are identified should be promptly repaired by a qualified electrician. When working with electrical systems, it is always important to follow safe work practices. This includes wearing appropriate personal protective equipment, such as safety glasses and gloves, and using insulated tools. It is also important to de-energize the circuit before working on it, and to verify that the circuit is de-energized using a voltage tester. If you are not comfortable working with electrical systems, it is best to hire a qualified electrician to do the work. The electrical work can be dangerous, and it is important to take all necessary precautions to protect yourself and others from harm. In summary, selecting the correct ground wire size for a 200 amp electrical service is crucial for safety and compliance with electrical codes. The ground wire must be the same size as the phase conductors or larger, and it must be properly installed and maintained. Using an undersized ground wire can create a significant safety hazard, increasing the risk of electrical shock, fire, and damage to electronic equipment. Consulting the NEC and hiring a qualified electrician are essential for ensuring that the grounding system is properly designed and installed. Always prioritize safety when working with electrical systems, and take all necessary precautions to protect yourself and others from harm. Furthermore, it is essential to consider the specific requirements of the local electrical codes and regulations. These codes may have additional requirements for grounding systems, such as the type of grounding electrode system that is required or the minimum size of the grounding electrode conductor. It is important to consult with the local electrical inspector or a qualified electrician to ensure that the grounding system meets all applicable requirements. The type of grounding electrode system that is used can also affect the size of the grounding electrode conductor. For example, if a ground rod is used as the grounding electrode, the grounding electrode conductor must be at least number 6 copper or number 4 aluminum, regardless of the size of the service entrance conductors. This is because ground rods have a limited ability to dissipate fault current, and a larger grounding electrode conductor is needed to ensure that the fault current can be safely carried back to the source. If a metallic water pipe is used as the grounding electrode, the grounding electrode conductor must be sized according to NEC Table 250.66, based on the size of the service entrance conductors. However, the grounding electrode conductor is only required to be connected to the metallic water pipe within 5 feet of where the water pipe enters the building. If the water pipe is not accessible within 5 feet of where it enters the building, an additional grounding electrode, such as a ground rod, must be installed and connected to the grounding electrode conductor. It is also important to consider the impedance of the grounding path. The impedance of the grounding path is the total opposition to the flow of fault current from the equipment enclosure back to the service equipment. The lower the impedance of the grounding path, the more effectively the grounding system will protect against electrical shock and fire hazards. The impedance of the grounding path can be affected by several factors, including the size and length of the grounding conductors, the quality of the connections, and the type of grounding electrode system that is used. To minimize the impedance of the grounding path, it is important to use properly sized grounding conductors, make clean and tight connections, and use a grounding electrode system that provides a low impedance path to ground. In addition to the grounding electrode conductor and the equipment grounding conductor, there is also a bonding conductor. The bonding conductor is used to connect together all of the metallic parts of the electrical system, such as the metal enclosures of equipment, the metal conduit, and the metal water pipes. The purpose of the bonding conductor is to create a low impedance path for fault current to flow between these metallic parts, which helps to prevent voltage differences from developing between them. Voltage differences between metallic parts can create a shock hazard, as a person could come into contact with two metallic parts that are at different voltages. The bonding conductor is sized according to NEC Table 250.102, which is based on the size of the service entrance conductors. It is important to ensure that all of the metallic parts of the electrical system are properly bonded together to minimize the risk of electrical shock. Furthermore, surge protective devices, SPDs, can be an important addition to our home's electrical system, providing protection against transient voltage surges caused by lightning strikes, utility switching, and other events. SPD work by diverting surge current away from sensitive electronic equipment, protecting them from damage. When used, they must be properly grounded to function effectively. The grounding conductor for the SPD should be as short and straight as possible to minimize impedance and ensure that the surge current can be safely diverted to ground. SPD are typically installed at the service entrance to protect the entire electrical system, as well as at individual branch circuits to protect specific equipment. The selection and installation of SPD should be done by a qualified electrician to ensure that they are properly sized and installed. Another important aspect of grounding is the use of ground fault circuit interrupters, GFCIs. GFCIs are designed to protect people from electrical shock by detecting ground faults and quickly interrupting the circuit. A ground fault occurs when current flows through an unintended path to ground, such as through a person's body. GFCIs work by monitoring the current flowing in the hot and neutral conductors of a circuit. If there is a difference of more than a few milliamperes between the current in the hot and neutral conductors, the GFCI will trip, interrupting the circuits and preventing electrical shock. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas, where there is a high risk of electrical shock. They should be tested regularly to ensure that they are functioning properly. The grounding system plays a critical role in the operation of GFCIs. The grounding system provides a path for fault current to flow back to the source, which allows the GFCI to detect the ground fault and trip. If the grounding system is not properly installed or maintained, the GFCI may not be able to detect a ground fault, and the person may be exposed to electrical shock. Therefore, it is essential to ensure that the grounding system is properly installed and maintained in order for GFCIs to function effectively. Regular maintenance of the grounding system is also important. Over time, connections can become loose, corroded, or damaged, which can increase the impedance of the grounding path and reduce its effectiveness. Regular inspection should be performed to check for any signs of damage or corrosion, and any problems should be promptly repaired. Connections should be tightened, corroded parts should be cleaned or replaced, and damaged conductors should be repaired or replaced. In areas where there is a high risk of corrosion, such as coastal areas, special precautions may be necessary to protect the grounding system from corrosion. This may include using corrosion-resistant materials, applying protective coatings, or installing sacrificial anodes. By performing regular maintenance, the grounding system can be kept in good condition, ensuring that it will continue to provide effective protection against electrical shock and fire hazards. Furthermore, understanding the difference between grounded and ungrounded electrical systems is important. A grounded electrical system is one in which one of the conductors, typically the neutral conductor, is intentionally connected to ground. This provides a reference point for the voltage in the system and helps to stabilize the voltage. It also provides a path for fault current to flow back to the source, which allows overcurrent protective devices to operate and prevent electrical shock and fire hazards. An ungrounded electrical system is one in which none of the conductors are intentionally connected to ground. In an ungrounded system, a ground fault will not cause the overcurrent protective device to operate, as there is no path for the fault current to flow back to the source. However, an ungrounded system can continue to operate even with a ground fault, which can be an advantage in some applications. Ungrounded systems are typically used in industrial and commercial applications where it is important to maintain power to critical equipment. However, ungrounded systems are generally more complex and require more sophisticated monitoring and protection devices. In most residential applications, grounded electrical systems are used due to their simplicity and safety. The grounding system provides a reliable path for fault current to flow back to the source, which helps to prevent electrical shock and fire hazards. In conclusion, ensuring proper grounding is not merely about adhering to codes, it's about safeguarding lives and property. From selecting the correct wire size to maintaining the integrity of connections, every aspect of the grounding system plays a vital role in electrical safety. Regular inspections, proper installation, and adherence to the NEC guidelines are paramount for a safe and reliable electrical system.